Engineering Director Jack Humphrey stands next to a projected title slide that reads, From 1 to 1 billion, Evolution of a Document Serving System. Engineering.indeed.com/blog, on Twitter @IndeedENG.
My name's Jack Humphrey, and I want to start out by giving you a quick overview of what Indeed does. So our core product at Indeed is a search engine for jobs. We aggregate all the job postings around the world, and we bring them together and make them searchable for job seekers. Our watchwords at Indeed are simple, fast, comprehensive, and relevant. These principles inform how our products work. Job search has a simple user interface for job seekers. It's blazingly fast so that those job seekers can quickly find what they're looking for. And it's comprehensive. We want all the jobs, not just some of the jobs. And we want the jobs that we give to our users to be relevant to them. So these principles inform how all of our products work, but they also inform how we work on our products. Simple and fast are things that we think about a lot when building solutions. We want to choose the simplest solution that works for the requirements, and we want to get that built fast. We want to iterate quickly, get things in front of users, and continually improve.
Slide, Indeed.com Stats.
Our job search at Indeed is in over 50 countries, in 26 languages, and we just celebrated a great milestone in our history. We now have over 100 million unique visitors worldwide every month, doing, as Doug mentioned earlier, over 3 billion searches. We are the largest job site in the world.
Indeed homepage.
Quick tour. Our homepage has a what and where box. It's very simple. You tell us what you're looking for and where you're looking for it. If I start typing software engineer, I'll type a few letters, and it'll make some suggestions to me. The first one's software engineer, so I accept that and do that search. And I get back some search results. These are jobs, and in fact, I'm looking at the first 10 of over 100,000 for software engineer in the US. This is sorted by relevance, but I can click a link on the left here and get it sorted by date, so the newest jobs come first. And this is a really important point for us at Indeed. We want jobs to be as fresh as possible. Freshness really matters. So from the time we find a job on the internet to the time it's live and searchable by our job seekers, we need that to be as fast as possible. And in fact, you can't probably read the screen here, but the top job for its age says 8 minutes ago. So we're always trying to push that number lower and lower. If I limit the search to software engineer in Austin, Texas, I narrow it down a lot. Now I'm getting a little under 2,000 results, down from over 100,000. And if I click on some of these jobs, I'll probably see a page like this. We call this our view job page, and this just gives the full job description. And in this case, is highlighting our Indeed Apply functionality that lets you apply to a job without leaving Indeed. And this job just happens to be a job here in Indeed, but the Indeed Apply functionality can work for any job on our site. So I said fast is one of our watchwords. Speed, we think speed is a feature. And as a quick sidebar, we log everything that we do. All of our products are always logging lots and lots of information into our logging architecture, on top of which we've built some great analytical tools that allow us to interactively ask how different metrics are doing over time. So I've used those tools, and I've pulled some numbers that will help me illustrate how fast job search is. The first graph I'm going to show you, this is the time we spend on the server generating search results. And so this is just the time that it takes from getting the search to assembling the search results page and starting to send it back. And the median time for the US, the hourly median time, you can see here over the last couple of weeks, is around 90 milliseconds. So that's nice and fast. We are pretty happy with that, but we're always pushing to keep that as fast as possible. But we care more about more than how fast our search results are generated on the server. We care about what users are actually perceiving. So we've implemented a JavaScript beacon that lets us approximate how long it takes really for a user from asking for the search to getting back the search results page and it being visible in their web browser. So this is that metric. I'm calling it perceived time. And again, we're looking at the median is around, for the last couple of weeks, is around 450 milliseconds. So that's well beneath a second, which is where we always try to keep job search.
grabperf.org, search performance index with Indeed second to Google.
GrabPerf is an independent third-party distributed performance measurement. They have points of presence around the world, and they constantly measure response time for a bunch of different sites. And if you go there, you can see the average response time from all these different places around the world for the last 2 hours. They organize things into categories, and in the search engine category, we find that we're typically very close, or right around the top of this list. And when I took this screenshot the other day, we were second only to Google. So we're always pushing. We're happy to be at the top of this list, but we're always pushing to get faster and faster. They also look at availability or uptime, and that's something that's very important to us too. We strive really hard to make sure that our site is never down, that when job seekers come, our site is always working for them.
Slide, where we started.
So today, I'm going to tell you a story of how a key part of our infrastructure evolved over the years. And if you take away one thing from what I'm going to talk about, I want it to be that we really believe in aiming for simplicity. We believe when we build solutions, we build for the scale that we expect, and we keep it as simple as possible, and we iterate. And that's kind of the pattern that you'll see in the story that I'm about to tell. As I get into some of the details, some of the specific technology solutions may seem dated, because they are. I'm going back 8 years in time. But it's really the pattern that I think is interesting. It's allowed us to evolve our software in a cost-efficient way as our traffic has grown. Another note about the story I'm about to tell, at each inflection point in this story, you might think to yourself, well, why not just throw more hardware at it? Why not get beefier servers or more servers? Wouldn't that work to solve this problem Jack's talking about? And there's a lot of different good reasons that that's not how we've approached problems along the way. But I think maybe the best is that we wanted to be profitable as fast as possible. And that seems like a good reason to me. Keeping those hardware costs down helped us get there sooner. And in fact, if we look at it in retrospect, where we are today, if we had taken that approach, our hardware costs would probably be like 100x what they are today, and we probably would have had to still solve a lot of the same software problems along the way to get there. So the title of the talk is From 1 to 1 billion. Where does the story start? Well, the first search would have been back in 2004, in December 2004, when we launched. In the first month, we went and aggregated a couple million jobs. We got to a peak serving point of serving up 160,000 job documents per day, with the peak second being around 7 job documents served in the peak second.
One search, all jobs.
So how did we build that first version of job search in 2004? One of the first technology choices made was Lucene. And Lucene is a great open source tool that allows you to index documents and their fields and make them easily searchable. It works, it's fast, and it's been a great tool for us. We feed our job data in, and it lets us search all the jobs. So at its core, Lucene is giving back for a given query, is giving back a set of document IDs. And once you get back those matching document IDs, you actually have to then get some meaningful data to display to the user. And that's the problem that we're going to talk about today, displaying all the jobs, which we call document serving. And going back to our watchwords from the beginning, the watchwords for document serving are probably fast and comprehensive. We want to get jobs searchable on our site as fast as possible, and we want the document serving portion to be able to serve those documents up as fast as possible. And we want all the jobs to be searchable.
Document serving, sample software engineer search result.
So here's an example search result on Indeed. Typically, we show 10 of these per page, and they've got to load really fast. There's a few different fields of the documents that we're serving that I'll highlight. There's the title of the job, the company, the location, which in and of itself is made up of subfields. It's structured data in and of itself. The snippet, which is derived from the job description, and the job's age. Those are just a few, but kind of the most visible when you look at a search result page. So how did we implement this? We let Lucene do it. More specifically, we used stored fields, which is a very common approach with Lucene. And if you use Solr or Elasticsearch nowadays, and those are based on Lucene, it's very common to use stored fields. Basically, when you're indexing your documents, you tell Lucene, index them and build your efficient indexes, but also just store the field data of the documents directly in the index so that I can ask for it later. This works, and it worked for us.
Lucene workflow diagram.
We had an index builder that ran periodically every few minutes and looked at new job data in our database and wrote a Lucene index, which then we shipped over to our web server using where our search web app was running using rsync. Then the search web app loaded in the Lucene index and did both the search and the document serving all using Lucene. It worked. Job search was fast, results were fresh, we were happy. If we fast forward to about a year later, if my clicker works, yikes, worked too well. Okay. If you remember, we were, when we launched, we were at about 160,000 documents served per day at peak. By about 11 months later, in November 2005, we were up to 5 million documents a day being served, with a peak second of about 100 per second. And we doubled, more or less doubled the number of jobs that we were aggregating each month.
3.9 million new jobs.
So great, awesome. Really happy to get that growth. And what did that mean for us? What problems did we start to run into? Well, as the job index grew, we started to notice some problems, specifically with Lucene Performance and how Lucene works with your operating system's I/O cache. Lucene depends really heavily that your file system cache, your in-memory file system cache, be big enough to hold the entire Lucene index in memory. Once your index is bigger than your available RAM, it starts swapping pieces of the index out and performance degrades really fast. And in fact, our first engineer, Chris Lampert, who's sitting in the back there, hi Chris, he noticed that when our index got up into the 6 to 7 gigabyte range, that on these commodity hardware servers we were running on that had 4 gigs of RAM, performance was degrading. And looking at the index, you could see that stored fields were the bulk of that index size. We also wanted to keep our job data around forever. We wanted users to be able to permalink that view job page that I showed you earlier and come back to it at any point in the future, even after the job had fallen out of the search index. And we actually could use a database to do that, could use an archive database to do that, but that would mean two code paths for job serving, for document serving. The code path to use Lucene stored fields and the code path to use the database. So we had some problems. We decided to switch the implementation from stored fields to using the database. This made sense. Our aggregation processes were already writing to a MySQL database. It was on a different server that had dedicated resources. It was a more powerful server. It had indexes, so looking up a job by job ID was super fast. And it did aggressive caching. It kept recently accessed job data in memory, and that was nice. That helped us a lot with speed.
Workflow diagram.
So now our picture changes only slightly. Now we're only pulling search results from our Lucene index, the document IDs, and then going to the database to get the actual job data to display. So that worked. Job search was fast again, and results were fresh, and we were happy. So again, November 2005, we're serving 5 million documents a day. Fast forward a year to November 2006. Now we're up to 4 times that, 21 million documents a day in the US, and with a peak around 500 per second. We were, I think, aggregating about 5.2 million new jobs a month. And this traffic growth continued into 2007, and we soon had to address a key problem, which was write contention on this database that we were using. So as we got more and more job updates, and we were writing, our aggregation processes were writing this job database more and more. They were writing to one main job data table. And this table used the MyISAM storage engine in MySQL. instead of the InnoDB storage engine in MySQL. And the key part of that that's important is that MySAM uses table-level locking, which meant that when our aggregation processes were updating the job data table, they were locking out the search web app from reading that data. And conversely, when the search web app was reading job data from the table, it was locking out the aggregation updates. So that's not a good thing. So you might say, well, can't you use MySQL replication and have the search web app read from a replica or a slave in MySQL terminology? And you know, we investigated that. We looked into that. We tried that out. The issue with that, actually, is that it causes replication delay, which may not be immediately obvious why, but MySQL has a replication system that's single-threaded. There's one thread that's writing updates to your replica. And if this table that it's updating is a MyISAM table, it's subject to the same locking that I just talked about, which means that if we have lots of search web apps reading off of that table, they're locking out that update thread that's doing the replication. That means that that table falls far behind. And when that table falls far behind, now we get into a situation where we actually have jobs potentially in our Lucene index that we can't display. And so freshness suffers, and that's a bad thing. So and another point would be, why not just switch to InnoDB? And there are a lot of reasons that we didn't immediately switch to InnoDB. We actually eventually did switch to InnoDB. But we needed to solve this problem sooner than we could switch to InnoDB.
Caching to the rescue.
So we turned, as we saw that reading from the master database was going to be no longer tenable for us, we switched to application caching. And specifically, we used Memcache. And we did this in 2007. Memcache is an open source, high-performance memory object caching system. And it's very simple to use. It's a very common approach for alleviating database load. Great.
Workflow diagram.
Also in this time frame, we started our evolution to a service-oriented architecture, and we built a service we called the Dock service, which ran on its own server. And actually, the search web apps would talk to it, and it would handle all the aspects of document serving. This communication was initially over HTTP. In later years, we moved it to our own service infrastructure we built called Boxcar. I'd love to talk about Boxcar now, but that's not what this talk is about. And actually, we have a blog post on engineering.indeed.com from last December that goes into a lot of details about Boxcar. So if you're curious about that, I encourage you to check it out. So now the Dock service is talking to the Memcache. And it's looking in the Memcache and only falling back to the database if it can't find a job in the cache. And actually, what we could do is prime that Memcache from the database with as many jobs as we could fit into it. And then we could get up to a point where basically we were hitting the Memcache 99% of the time and hardly ever having to go to the database. So that's great. We were also, with a background thread in the Dock service, sort of tailing the job database, if you will. We were looking at new and updated jobs and putting those into the Memcache as we ran. So we would really avoid those cache misses and not have cache misses affect the end user experience. So Memcache was great. It worked. Job search was fast, and results were fresh. We were happy. We got from 21 million documents a day in 2006. Fast forward 2 years to November 2008, we're up to 150 million documents being served per day with a 3,000 per second peak. And at this point, this is really just looking at our US site. And by this point, we were in half a dozen countries. And we knew that in 2009, we wanted to massively expand our worldwide presence. But first, we had to address some key problems. For one thing, we were still depending on the database. We weren't always going to it anymore. But when we did, we were still subject to that same write contention. And the processes that were reading and updating the Memcache in the background were subject to that. And as an example, I think in late 2008, there was a very large aggregation update that touched 21,000 jobs in the system. And it locked that job data table that I mentioned before for 41 seconds, which caused cascading failures and kind of impacted end user performance and freshness. So that wasn't acceptable. We also found that actually doing the priming of the memcache became basically impossible because we had to do it very slowly. We had to sort of trickle the jobs out into a new memcache when we wanted to bring it online. Otherwise, we would create all that contention and lock out aggregation again. And that got to a point where I think we did an estimate and said, okay, bringing a new memcache online is going to take 36 hours. We need to do something else. Also, we found that we were needing more and more data from the database that we weren't able to get. We had started collecting more data in the aggregation process that was properly normalized into other tables, and we didn't really want to be doing table joins on MySQL to get the data out. And we were doing a lot of post-processing that was actually writing to entirely different databases, but had useful data about jobs. An example was job language. So a lot of times we know the job language in our aggregation processes, but sometimes we were actually running processes that detected the language based on the job description. And that was going into another table. And as we were launching in more languages, it was actually very important for us to present the job properly to know what language it was in. That's just one example, but there was a lot of data that we were looking for that we couldn't use because we didn't want to do more joins or more queries on the database. We also, as I mentioned before, wanted to expand our worldwide presence, and we were bringing on new data centers around the world, in Europe, Asia, Australia, and we needed to do this without depending on a central database or taking the hit of trying to replicate that database out across data center. So our challenge, to summarize, was we needed to get all the job data that we wanted, and we needed to get it in one place. We needed it to be easy to replicate to these remote data centers and extremely fast to access for document serving. So what was our solution? More caching. We built something we call the Dockstore, and it is a dedicated denormalized store that's optimized for reading. It is basically a serialized file system cache. We took the job data and we wrote it into files on the file system that we could then look up the job data based on job ID quickly. It was another level of caching. We kept memcache. Memcache is super fast and works great. So if something wasn't in the memcache, we would fall back to the Dockstore. If it wasn't in the Dockstore, only then would we fall back to the database. We wrote the job data to disk in segment files of up to 100 jobs. We used Thrift to serialize them, and we compressed them.
Dockstore example, sample 9-digit job ID referencing directory, file, and offset.
And we used a file system structure to make lookups efficient. We took the job ID and we sort of segmented it and said the first few digits take you down one directory. So in this example, 7 gets you down one directory. The next 3 digits, 936, get you down another directory. 277 gets you down to the file name. And the last 2 digits, 89, give you the offset into that segment file. So this was important because we knew that if we tried to put too many files in a single directory, we would run into index scanning issues. Even on efficient file systems that use efficient data structures for indexing, you don't want to get thousands and millions of files in a particular directory.
Dockstore structure diagram.
So here's a review of kind of what this structure looked like. And the key point here is that everything was serialized to disk sequentially based on job ID. That will be important later. So I want to point that out.
Dockstore workflow diagram.
So we built our Dockstore by having a Dockstore builder that ran on a server and watched the job database for updates and wrote the Dockstore out. We then replicated that Dockstore using rsync out to the remote servers that were either in the same data center or remote data centers. And we were able to actually, then the doc service could actually use this Dockstore as a fallback, as I said. If something's not in memcache, it goes to the Dockstore. If it's not in the Dockstore, it goes to the database. And now we were able to prime that memcache not from the database, but from the Dockstore. So both bringing a new memcache online and keeping it full and warm with new job updates could happen entirely from the Dockstore. We also implemented changes in this time frame to allow us to exclude jobs from search results that weren't yet in the Dockstore. This meant that we could get rid of the database dependency entirely and never fall back on the database. This was very important in some remote data centers where we definitely did not want to replicate our MySQL database out to them, and we didn't want to take the hit of trying to do a remote MySQL query from them back to a central database. So the Dockstore worked. Job search was fast and results were fresh. Again, November 2008, pre-Dockstore, we were serving 150 million documents a day in 6 countries. Fast forward a little more than a year, we rolled out the Dockstore in 2009, and by January 2010, we were serving over 300 million documents per day in 23 countries with a peak that's double the previous peak of 6,000 per second.
22.5 million new jobs.
So that's great. Dockstore is making us happy. And I'm going to fast forward again in time to November 2011, just to show you how our traffic increased in that time frame. We were getting close, 850 million, starting to get dangerously close to 1 billion documents a day with a peak of 14,000 a second. And at this point, because we'd brought on all these new countries, finding all these new jobs out there, we were up to 32.5 million new jobs a month. So what challenges did the Dockstore face as traffic grew to these levels?
Random I/O.
Well, one problem comes from the fact that the jobs, an individual job storage location is based on job ID, as I showed you before, meaning for a given job ID, there's a file you have to find if you're going to update it. Now, if jobs were immutable and written once, then this would be okay. But in fact, we know that jobs get updated. Jobs aren't just written once. And so in our measurements, we see that there's 1.5 writes on average per job, which means there's a significant percentage of jobs that are going to be touched after they're initially written. This means that writes are going to random locations in the Dockstore at any given moment. And that resulted in, among other things, slow replication. When we are seeing those updates out, they're also doing all those writes to random locations. We also found that it was hard to detect and recover from errors like file system corruptions, maybe resulting from servers going down unexpectedly. It was just basically hard to detect that it had even happened, and when we did detect it, it was difficult and time-consuming to recover from it. At a basic level, updates to the Dockstore were slower than they really felt like needed to be. In order to update a job, you had to find its segment file, you had to decompress it into memory, update the job data, recompress it, and write it back out. And as our job volume increased and we launched in more and more countries, we were seeing such a high write volume with all these disk seeks that were required to write to various places on disk that it became too high for a single drive to keep up. So as we scaled up more and more, we began to feel the pain of some of these aspects of the Dockstore, and it was time to do something new. And it was time specifically for Dockstore v2. And I'm going to hand off now to Jeff, who wrote Dockstore v2, and the clever data structure called the log-structured merge tree that it's based on. And he's going to tell you how that works.
Jeff Plaisance, software engineer.
So let me get into it.
Dockstore v1 structure diagram.
So just to recap, Dockstore v1 was this directory hierarchy with these files in the directories, and then within the files there are these jobs. So I really want to kind of drill down to what the real problem is, which is that updating one of these jobs meant doing a whole lot of I/O. So we have to read the job, or read the file, update the job, rewrite the file, and that involves doing usually 2 disk seeks, one to read and one to write it again. So that kind of limits how much we can do.
Disk I/O numbers, table detailing numbers for disk seek, sequential disk bandwidth, average job size, job throughputs, and disk bandwidth.
So from the basic perspective of what can a magnetic hard disk really do? A magnetic hard disk can do a seek in about 10 milliseconds. It can write about 30 megabytes per second, and then, so that's kind of the performance numbers on a hard disk. Our jobs, when they're compressed with LCO, they're about a kilobyte. So then if you just look at that sequential disk bandwidth number, that kind of tells you that we can do 30,000 job updates per second. Well, not if you're doing those seeks. That sort of limits you to 100 seeks in a second, and if each of those updates requires a seek, you're sort of limiting your throughput to 100 random reads or writes. And then when you're looking at the actual disk bandwidth you're getting at that point, you're doing 1 kilobyte of I/O 100 times per second. So you're really not getting good utilization on your disk.
Overview of a job posting.
So 1 kilobyte job postings, optimal is 30,000 updates per second. What were we really getting? A maximum of 37.5 updates per second, because that's the time that it takes to seek to do the read. Then you do the read, you do the update, you do another seek, and then you write it back. So the 200K of I/O and the 2 seeks means you can only do a few updates a second, and then that's really not optimal when it comes to what your potential throughput could be. So sort of like from a general perspective of doing I/O on a disk and scaling any sort of service like this, like a document storage service, scaling reads is really not a hard problem. It's a well-solved problem. The way you scale reads is you throw more replicas at the problem. You throw more memory at the problem. You use memcached, you do caching. It's pretty easy, but scaling writes is not very easy. If you have a single server and it can't keep up with the write load you're trying to get through, there's no amount of replicas you can throw at it that will fix that problem for you. So you need to sort of fundamentally fix the data structures that you're using to do those writes so that you could scale your write load by throwing more replicas at it. Your read load by throwing more replicas.
Key insight: reads are random, might as well optimize for write performance.
So another point here is that we don't really know what our read workload looks like. So we're getting these reads in, and then we've done all these writes already so that you can go back and look up these documents based on these IDs. But going into it, when we were doing the writes initially, we didn't actually know that people were going to do like sequential accesses on these. So why are we really writing them sequentially into these files? So we're writing these files with 100 jobs, and they're all grouped together by these keys, but we're trying real hard to make sure that these 100 jobs are in this one file when we're not going to access them that way. So we have these random reads. So how can we optimize our writes? Well, we could just do all our writes sequentially. If we did all our writes sequentially, we could go back to that 30,000 updates per second number I was getting to earlier, and then that really throws this problem way into the future when you can't, when we're getting that many jobs. We're not there yet, unfortunately. So the trick is going to be convert these random writes into sequential writes. And once we've done that, we're going to be able to scale this pretty far into the future. So big picture, what do we have?
Workflow diagram from aggregation to doc service.
We've got aggregation. They're going out and getting jobs. They're putting them into this database, and then we're going to build this thing called the Dockstore queue. So this is going to be all of the new and updated jobs written sequentially to some files. We're going to replicate that to our remote data structure. We're going to build an index on top of that, and then we're going to use that to serve out the jobs. So the first thing we're going to talk about here is the Dockstore queue. It's pretty simple. It's just sequentially numbered files on your hard disk, and the files each contain a set of jobs. So within each file, which we call a record file, there are blocks, which are the actual unit that is compressed. So there's sort of an address for each of these blocks within the file that you can seek to very, very quickly. You can seek just straight to that block. And then within the file, you decompress that block, and then there's sort of an offset table for which, like if you want the third job in that block, you look at what is the offset of the third job, and then you just sort of jump there, and then you can read that job. So we kind of have like this constant time access to the jobs by this address number. So all we have to do at this point, then all we have to do at this point is build this index from a job ID to an address in this record log. And as Jack was saying, as we only get an average of 1.5 writes per job, so one write and then maybe a 50% chance of an update per job, we can just keep that Dockstore queue around forever and then go back based on these addresses from this job ID to address map. So then the next thing we're going to talk about is how can we build an index that only does sequential I/O? So like a B tree doesn't do that. That's random. The thing we had before doesn't do that. That's totally random.
InMemory Index.
So let's just keep it all in memory. Let's see where that gets us. So that little picture there is supposed to look like a binary tree. So hope it does. We're reading our Dockstore queue, and then we're building this index of job ID to address in memory. So we're good so far. We have a small amount of data. It works.
Tree expands to 4 branches.
We add more. It gets bigger.
Tree continues to expand exponentially.
More. We get more. It's really big. And then all of a sudden, we have a big problem. We ran out of memory. The OutofMemory Killer started on our server, and now we've got to hard restart the thing and just start over. So that's no good. This is not going to work. This is not going to scale unless you just continuously throw memory at your server forever. And at some point, that's just not going to work anymore.
Basic merge.
So let's see what we can do once our InMemory Index starts to get slightly too big.
Binary tree expands to 8 branches.
So, we're going along like we were before, making this bigger and bigger thing. And then why don't we just take what we have in memory right now and flush it out to disk? And then start a new InMemory Index. So let's see where that gets us.
1 write per batch.
So now we have this on-disk index, and we have an in-memory index. All the updates go to the in-memory index, and then on a read, you check the in-memory index. If it's not there, you check the on-disk index. So that seems like it would scale pretty well. And then I just want to point out that there's a number on the on-disk index, which is going to change as I go through these slides. But what that is it's the number of times as the blue set of jobs has been written to disks. As you may have noticed before, the jobs in memory, that binary tree was sort of blue. So these are the blue jobs is what I'm going to call them. Now let's start adding some more jobs. They're slightly different color blue.
Binary tree expands to 4 and 8 branches.
I think they call that cyan for designers or something, I don't know. So then we add more and more. And now we have a problem because we have this on disk index, we have this thing in memory, and we're really out of memory, but we already have an on disk index. So what are we going to do? Well, you can do a sequential merge of these two data sets. They're both sorted. So let's just do a merge and then write a new on disk index and see where that gets us. So that's what that gets us. And then we've written the blue jobs twice. We've written the cyan jobs once. And then we have a new in-memory index. And then our read performance is sort of the same as we were with the single. We still have a single on-disk index. So then we can do this again.
Green binary tree grows to 8 branches.
And then we're going to merge again.
3 blue, 2 cyan, and 1 green writes.
And then we keep writing these things. And then we do it again. And then, as you can see, that number of times the blue jobs have been written just keeps going up by 1 every time we have to merge. And then the rest of them keep going up by 1 also. If you do the math on this, that works out to the number of batches of jobs you write, the number of times that you end up flushing each segment back to disk when you do this merge goes to n for each segment. So for all the segments, it goes to n squared. So we kind of get n squared writes. So as you keep going down with this, it's going to be a problem. You're not going to be able to keep doing these merges in a reasonable amount of time each time you fill up your in-memory buffer. So that's not going to work. That's not going to scale. So then we can consider, why are we even doing this merge in the first place? There's a good reason for it, But if you look at where we are here, what we were doing is we're reading that InMemory index, then reading the on-disk index. So let's just like flush a new on-disk index and keep the one we had before so that we're not copying it every time. So if we do that, then we get like that. And then we would read the on-memory index, then we'd read the next on-disk index in line, and then we'd read the on-disk index in line after that. So let's just keep doing that and see where that gets us.
One write for each batch.
This clearly doesn't scale either because the reads approach order n for each one, order n in the number of batches of jobs that you flushed. So that's not going to scale either because way down the line, when we have 1 billion jobs in here, if each batch is like 100,000 jobs or something, like it's really not. You're going to have to read so many different indexes that it's not going to scale at all. So let's not do that. Instead, let's do something smarter with the merging.
LSM-Tree.
The solution here that I'm going to present is something called a log-structured merge tree. Sort of the idea behind a log-structured merge tree is that it's a key value store, but it's hierarchical. And like I was saying with the previous indexes, the newer ones are the ones you read first. The older ones you read later, if you don't find it in the newer ones. And the way that you build a log-structured merge tree is sort of the innovation. It's built through incrementally merging these similarly sized indexes. So you're not always going to take your big index with everything in it and merge this little update into it every time. You only want to merge if things are similar in size. So, and this is a data structure that's going to be both efficient for reads and writes. So that's sort of the claim I'm making, and then I'm going to explain why that is.
LSM-Tree.
So this is where we were sort of in the beginning. And then we get back to the point where we have to make the decision to flush.
Tree expands to 8 branches, 1 write for the batch.
So let's do that. We flushed our first in-memory index to an on-disk index. This was always fine. This has never been a problem for us yet. So let's see. This is the point at where we have to make a decision. What do we do with this in-memory index? So I'm going to introduce a concept called compaction. The idea of compaction here is that if we only merge the on-disk indexes, all of them, so we're going to have multiple eventually in the scheme, if we only merge all of them when we've doubled the size of our data set, then each individual batch of writes is expected to take log n amortized time. So now let's see what we would do here. Well, here's something I'm going to call the compaction heuristic.
Index code.
So we've got an index that we're compacting to. We're going to call that the new index. It's the index that we're creating because our in-memory index filled up. So we're going to sort of build up these indexes that we're compacting. So we're going to say, while the sum of the sizes of all the indexes that are being compacted into our new indexes, while the sum of those sizes is larger or equal to in size to the next on-disk index. So the next one in line to the next newest, we're going to pull that disk index out of the disk indexes list and put it into the set of indexes that we're going to compact into this new index. So, and once we find one that's too big there, we're going to stop and we're actually going to do the merge and compact step. So we're going to do the merge and write that to disk, and then we have our new index, and then we'll replace all of those old on-disk indexes and the in-memory index with that new merged index.
LSM-Tree.
So what does that look like when we get to this step? These are equal in size. So by the compaction heuristic, that says we need to merge them. They're both size 1. So we merge them. But then we're going to get to this stage again, and then we have to make a decision. Do we merge or not? Well, the in-memory one is small. So it's smaller than the on-disk one, so we're not going to merge. So we're going to flush it out, and then we get here where we have 2 on-disk indexes and an empty in-memory index. Now, our in-memory index fills up again, and we have to make this decision again. And now we're going to compare the in-memory index to the first on-disk index. These indexes are equal in size, so our compaction heuristic tells us that we need to merge these. So those are going to merge, and then we look at the size of the merge result of that compared to the size of the next on-disk index in line. That is of size 2. And our merge result is going to be of size 2, so we should also merge those. So the result is this one big merged index after that step with 4 of our batches written into it. And we again have an empty InMemory index. So then our InMemory index fills up again, and now we have to make the decision of whether we merge. And the sizes are different. So the InMemory index is much smaller than the on-disk index, so we don't merge. So we flush again. So now we have 2 indexes again. So we fill up, we're getting towards full. Now we have to make the decision of whether to merge or not. And here, the InMemory index and the on-disk index are the same size. So we are going to merge. And then we compare the merge result size to the on-disk index size. And the merge result size is smaller, so we don't merge this one. So this is our result. We have 2 on-disk indexes now, again. And the newer one is bigger than it was before, but it's still smaller than the older one. And keep watching the numbers on each batch. This is how many times each of these has been written, as it was before in the previous image. And you can sort of see that each time we merge one of these, we merge everything, they only increase by 1. So that's the only case in which the oldest batch of jobs, that number goes up. So let's look again at what happens after this one gets compacted. So now the in-memory index needs to be compacted. But since it's smaller than the first on-disk index, we don't merge, we flush. And now we're to this one. This is the one that's going to cause the big compaction. Because once this fills up, we have to decide how to merge it. So we're going to merge the on-memory index with the on-disk index. They're of equal size, so we're going to do that merge. Then here we have the merge result compared to the next in line on-disk index. They're also equal in size, so we're going to merge that. Then we have to compare that result to the final on-disk index. And it's still equal in size, so we're also going to merge that last one. So we're going to do that merge, and we're going to end up with one really, really big on-disk index in which the oldest batch of jobs has only been written 4 times, which is the number of times we've merged that oldest index. So you can see as we do this procedure again, and the next time we merge this index with the other indexes, that 4 is only going to become a 5. So then you double again, it becomes a 6. So that kind of shows you that it's logarithmic, and the number of times that you've it's logarithmic in n, and each time you double it increases by 1. So the total time for doing all of these writes is n log n, which is sort of what you expect from a good algorithm for this sort of thing. So then here's sort of our big picture. We've designed this index that kind of tells us where to find these addresses for these job IDs. How does a user request actually access these data structures? Well, we get a read request in for a doc. So we look in the memcache. Let's say we don't find it. Then we go look in the in-memory index, and then we don't find it there. Since it's a binary tree, that is a log-in lookup. Then we go to the next on-disk index, and let's say we don't find it there either. Well, that was a log-in lookup. And then we go down the line to the next on-disk index, which is another log-in lookup. And then the last one is another log-in lookup. Sort of one thing that's important to point out is that there are going to be log-in levels of this LSM tree, which you can kind of see here with the decreasing sizes. So what do we do about that? So that works out to log-in lookups that each take log-in time. So that tends to go towards log squared of n, which is sort of a bad time complexity for a read on a key value store. If you have a B tree, that's going to be a log-in lookup. And so kind of decreasing that speed to log squared of n is not desirable at all. So we don't want that. So what we're going to do is we're going to introduce something called Bloom filters that allow you to optimize the lookups so that we can get back to that ideal login time. So what is a Bloom filter? A Bloom filter is a probabilistic set, and it has a function, a contains function like all sets, and the answer is different from a normal set in that it only tells you either maybe or no. It never tells you yes. So maybe means either yes, it's in there, or it might be in there. Who knows? But the no's are absolute, which is sort of the key to this working. If it tells you no, this item is not in this set, you know that it's really not there. Bloom filters are also very small. In our case, since our values are small and our keys are pretty small, the Bloom filter is actually pretty big compared to your normal Bloom filter, but it's still around 5% of the size of our total index. And they also have a low false positive rate. So a false positive is when it tells you maybe and the answer was really no. So the way we're using them here, they have a false positive rate of around 2%. You can tune that by using more memory. So what are our accesses going to look like with these Bloom filters? Well, first we're going to check the InMemory data structure. If we don't find the key there, then we proceed to the first Bloom filter. This Bloom filter is also in memory, so we check it. If it tells us no, then we skip the lookup in the next level, because this Bloom filter is a probabilistic set of all the keys in that level, and if it tells us no, we know the key's not there, so why look? So we skip that lookup, and another key insight is that these Bloom filters, the lookups are constant time. So it's a constant time lookup, so we've replaced a log-in lookup in the index with a constant time lookup. So then we skip to the next Bloom filter. So we do the lookup there in that Bloom filter. If it tells us no again, we look into the last Bloom filter. And if that tells us no, we know it's not in there. But if it says yes, we know it's in that last level. But assuming we don't get a false positive, we only ever look in one level, which is a single login lookup. So what this gets us is that we do login constant time lookups and a single login lookup. And the sum of that is still login. So that kind of gets us back from log squared of n to back to log n, which is sort of our ideal read complexity. But we kind of have a problem here, and that's that the Bloom filters only work if they're in memory. So yeah, I mean, we could keep buying more memory for our Bloom filters, but we really have a cap at any given time of how much memory we can dedicate to these Bloom filters. And we have a really tight memory constraint on our doc service machines because they've got this big mem cache, they've got this other stuff, and then the kernel needs RAM, everything needs RAM. So we can't go allocating like 2 gigs of RAM for a Bloom filter without knowing that that's not going to cause either swapping or the OutofMemory Killer to start running or something. So we want to be careful with our memory allocations. So we only want things to be in memory if we have room for them. Yeah, so we do have an upper bound on the memory usage that we can use for Bloom filters. So we pre-allocate, you know, say 2 gigs for Bloom filters or something. So let's say we're using 2 gigabytes. What can we do to put the most important parts of the Bloom filters into that 2 gigabytes? Well, we know that reading the Bloom filter on disk is slower than actually reading the index. Because if you've studied Bloom filters, you know that you do multiple random lookups. And if that's not in memory, it's going to be real slow because, for example, if you use 6 hash functions, you're going to be doing 6 disk IOs to read those things into memory. Reading the index is going to be like maybe 2 maximum, probably 1. So you don't want to be doing those random IOs in the Bloom filter. That's terrible. Another key observation is that no is the only useful answer a Bloom filter can give you. So you don't care about Bloom filters which tell you yes all the time, or maybe all the time. You only care about the ones that tell you no. Another insight is that if it's not in memory, like if part of your Bloom filter is not in memory, you can always assume that that part was just all ones. So that if you were checking that part of the Bloom filter, and I guess this is an aside here, if you're not familiar with Bloom filters, a Bloom filter is kind of like a bit set, except that the keys, like with a bit set, you can only put contiguous integers into that set. With a Bloom filter, you can put any keys into it, but imagine like taking a hash of your key and then setting that bit in the bit set. That would be your most basic Bloom filter. In reality, it's a little more complicated, but so when I say always safe to assume 1, that's what I mean, that 1 bit is set that you're looking for, that's the hash of the key. So if it's not in memory, you can always just assume it's 1, except that you really have multiple lookups, but you can assume the ones that aren't in memory are 1s. And then the last insight here is that the Bloom filters on the new levels are way more likely to tell you no than the older ones. So assuming that the key is in this data structure somewhere, since you have such a higher fraction of data on the lower levels, it's more likely that those filters will say maybe. So we can kind of see here what fraction of the data we expect to be in each level. So the InMemory index is an 1/8. The first on-disk index is an 1/8. The next on-disk index is a 1/4. And the lowest level is 1/2.
Limited memory.
So we can kind of see from that we expect the Bloom filter, like intuitively, we'd expect the Bloom filter on that first on-disk index to be the most useful Bloom filter. And sort of the way we're going to utilize these observations to sort of tune our Bloom filters is we're only going to keep in memory, in our limited amount of memory, what we deem to be the most useful pages. And what is a useful page? And we're going to assume all 1s for the other pages that we don't have in memory because reading them is too slow and it doesn't help us. What is a useful page, though, is we're going to have this usefulness rating, which is sort of like how many requests are we getting for that page, multiplied by the probability that that Bloom filter at that level is going to tell us no. And so how do we know what that probability is and what that usefulness rating is? So I'm going to start with this is going to be a little bit of conditional probability. Well, we can kind of see at our top level, 12.5%, so an 1/8 of the data is in that level. So we have an 1/8 chance of finding our key that is in this data structure somewhere. That's sort of a assumption going into this, is that the key is in here somewhere. But we have a 1/8 chance of finding that in that in-memory data structure. Well, if we don't find it there, then what is our chance of finding it in that next level? Well, it's slightly higher. It's 14%. And even though it's the same amount of data, that probability is increased because we've already discovered that it's not in that first level. But what was the probability that that Bloom filter at that first level told us no? Well, it's 84%, and it would be slightly higher based on the amount of data in that level. But it's decreased by the false positive probability here. And then as you keep going down, there's a lower chance that the next level is going to tell you no. And then there's a small chance or 33% chance that in that level you'll find the key you're looking for. And then in the last level, because we're assuming that the key's already in here, there's no chance the Bloom filter is going to give you any useful information. So the only reason to have a Bloom filter here at all is if you're looking for keys that are not in this data structure. And this will kind of help you a little bit in those cases. Whether you have this Bloom filter or not is really kind of optional. But yeah, so if you haven't found it yet, you have a 100% chance of finding it at this level, assuming it's in there. And then let's kind of look at the probability that we're going to even touch any of these filters. So it decreases each time based on the probability of finding the key at the previous level. So the probability of touching the first Bloom filter is decreased by the probability that we found the key in the InMemory Index. So then it's 87.5, so 7/8 chance of touching that Bloom filter at all. Assuming we don't, and then moving on, if we do find the key in that level, then that decreases our probability. But then we end up looking in the next level, and then so we have a 25% chance of having found the key at this point when we're checking the second Bloom filter. So we're checking this filter, and we have a 75% chance for a random key of checking that filter at all. And then for the last filter, the same thing, decrease it by 25%, and we have a 50% chance of checking this filter. Now that's our useless filter, so it's a 0% chance of telling us anything. But like, what does it look like when we are talking about the individual pages in these filters? Well, there's 2 pages in the first filter, and there's 4 in the second and 8 in the last, because they're doubling in size each time. So the probability of touching a given page in a filter is decreased by the fraction of, the percentage of that filter that's taken up by one page. So, if we take our 87.5% chance of accessing the first filter and we have 2 pages, then we have a 43.8% chance of touching any given page in that first filter. And then for the second level, we have an 18.8% chance, which is the probability decreased by a factor of 4. And then in the last, it's the probability decreased by a factor of 8. So as we move down, the probability that we touch a given page decreases even faster than the probability that we are going to be touching that page at all, touching that filter at all. And then if we multiply out these probabilities of no by our probabilities of touching a page, it kind of gives us our usefulness score for these pages. So then the pages in the first filter are way more useful than the pages in the next filter, which are way more useful than the pages in the last filter, because they're totally useless, assuming the key is in there. Now, we kind of go a step further here, and we don't assume that we're truly looking for random keys in this filter. So we're sort of assuming that maybe there will be some sort of locality here. So we actually keep account for each page of how many times we're trying to access this page. Because it's not random. It's usually sort of got a pattern to it. Like, you access one job, you're probably going to access it again in the future. So some of these pages will kind of be hotspots. So we keep account, and then we keep the usefulness, and then kind of multiply that together to get a total ranking for all the pages that could be eligible to be paged into memory for this Bloom filter. And then the ones we've deemed to be the most useful pages, those are the ones we actually load into memory and use for speeding up our searches in this data structure. So then another requirement of the Dockstore is durability. We want to be able to just take these Dockstore machines and just unplug them. That should not cause a problem. So that's pretty easy to do in this, it turns out. So here's where we were with the architecture diagram. We've got the LSM-Tree, the Bloom filters, memcache, and all that. Now, all we have to look at is what is actually not on stable storage here. Well, there's memcache, but that's just a cache. You can restore a caching layer from the underlying data structure. That's easy. Now, we have the in-memory part of the LSM-Tree. So that is not so easy to restore because it only exists in one place here. But what we can do is we can just add a simple transaction log that we write to the transaction log before we add things to this in-memory data structure. And then if we have a power failure, if we have a restart, you can just replay that transaction log to restore the in-memory state before continuing with normal operation. So we only have to add that one log, and we're to a durable solution.
Lies, damn lies, and benchmarks.
So then I've got some benchmarks, which I think are pretty cool. So what these are is it's doing 10 million operations. They're random operations, and they're 8-byte random keys and 96-byte random values. And so these are not going to have any sort of locality that sort of helps you. So the first one I'm going to go through is the write benchmark. So I've got the LSM-Tree, I've got LevelDB, which is another LSM-Tree implementation from Google. And then the last is Kyoto Cabinet, which is a B-tree implementation that is fairly popular. A lot of people use this. It's a pretty good implementation. So let's look at the write performance for doing these 10 million write operations. Well, the LSM-Tree that we wrote is the fastest at 272 seconds. LevelDB is 375 seconds for the writes, and Kyoto Cabinet is 375 seconds for the writes. This does not go along with what I told you earlier in this talk. You should be like, well, why is Kyoto Cabinet as fast as LevelDB when it's doing all these random writes? B-trees do all these random writes all the time, so why is this fast? Well, it turns out that it's about 100 bytes of data per operation, and at 10 million operations, that's only about a gigabyte of data. So that easily fits into the page cache of any modern machine. So you don't have to do these random reads before you do the writes. So here, Kyoto Cabinet is really getting a big benefit from the disk cache. But let's look at the read benchmark now. So the LSM-Tree that we wrote is again the fastest at 46 seconds to read these 10 million random keys that we just wrote. LevelDB is at 80, and Kyoto Cabinet's 183. So I don't know, I just like pointing out that ours is the fastest there. I don't really have much to say about this benchmark, but now let's look at another benchmark. And there's a Linux kernel feature called cgroups, which sort of lets you put processes into a group and limit their resources. So one of the resources you can limit is the page cache that is used by the processes in this group. So what I've done is I've limited this benchmark to use only 512 megs of memory. So that's less than our 1 gigabyte sort of expected memory usage from the size of our data that we're putting into this benchmark. So let's see what happens to our write benchmark if we run it again. Well, the LSM-Tree slowed down a little bit.
LSM-Tree 454 seconds. LevelDB 464 seconds.
LevelDB slowed down also, and now they're about equal. So any write speed up we gained is kind of equal it out when we're limiting the memory. But Kyoto Cabinet has slowed down to 50 hours. So that's a slowdown of about 400x, I think. And so that really illustrates this random I/O problem of doing these reads before you can do these writes. So, and I think the slowdown on the LSM-Tree and LevelDB is sort of due to when you're doing the merge, you have to read back in the on-disk indexes, and now you have to do these extra sequential reads for the on-disk indexes, which were previously already cached. So that's sort of how I think I can explain the slowdown there.
Kyoto Cabinet Block Dev I/O video.
And then I've got some kind of cool videos here. So what these are is you can think of this sort of like a four-dimensional graph where each pixel is a block on your block device. So moving across the x-axis would be sequential writes, and then moving down the y-axis is kind of like your sectors. And then as time progresses, each time an I/O operation touches one of these blocks, we're going to set the color of that block's pixel to the color of the current time. So the time is going to go from sort of like blue to red. So time 0 is blue, last time is red. And sort of like each time that block is touched, we're going to change the color of that pixel here. So you can kind of see how these different data structures are writing to the block device. Now these are on real block devices. This is not just something I made up. It's using a Linux program called BlockTrace to map the IOs, to watch the IOs and really draw this picture. And it's using ext4 as the file system on top of the block device. So this is a real benchmark, or a real visualization. There we go. Let me play this one. This is Kyoto Cabinet first. So if I'm not lying to you, this is going to look like pretty random.
Horizontal blue lines descend.
So it's writing some blue stuff. And then you can kind of see how it's going back and overwriting its data.
The lines turn cyan as they continue to descend, then green, yellow, orange, and red as speckles appear and become dense.
So it's really overwriting most of its data in this case because it's really doing random I/O. It's just going back and these new keys that are coming in that are next to those old keys that were there, it's got to rewrite that entire page in the B tree every time it does those updates. So this really looks like noise. I mean, it looks like random I/O. So that's kind of what you'd expect from that sort of thing. And then please go to the next slide.
LSM-Tree Block Device I/O video.
Okay, so here's the LSM-Tree one, sort of at a similar time scale. So
lines descend quickly in gradients of blue, cyan, and green, then again start from the top with yellow, orange, and red.
Well, that was pretty quick. So let's see that in slow motion. So you can see it writing. It's writing really sequentially. And remember, when any of these old on-disk indexes are deleted, it's not going to black out those blocks again. They're freed from the perspective of the file system, but it's not like telling you that they're freed. So it looks like it's using more space, but it's really not. The cool part is that this is actually the file system journal being written right here. And then you can see that it's really doing purely sequential I/O when it's doing these writes, which is pretty cool and kind of shows my point of what I was saying.
Recap.
And then just to go back through what I've kind of described, this data structure is doing all its writes as sequential IOs, and they're log n, amortized cost, and then the reads are log squared of n, but with this sort of Bloom filters hack, we get it down to log n again, which is sort of where we want it to be, with like a B tree is log n writes, log n reads, so we're kind of back to there.
Graphs, median total service time and median dock serving time.
And then what does this actually mean for our site? So what is our time? What is our server time on this site? So that's 90 milliseconds average for the search. What is the dock service fraction of that? It's only 5 milliseconds, and it's real consistent. You can kind of see how consistent it is throughout this time period. And then even if you get into the higher percentiles, so this is the median, but if you're talking about the 99 percentile, it's still pretty consistent. I mean, it's there or something, but this thing is pretty quick.
Dockstore v1 comparison.
So then, compared to the original version of the Dockstore, how much better are we doing? Like, have we really gained a lot? Well, Dockstore v1 took 12 hours towards the end of it in 2011 when we were like, we really need to replace this now. It took 12 hours to update its data structure on 1 day's worth of jobs. So if we got behind on replication, anything got held up at all, we were going to have a big problem catching up. It's going to take forever to catch up. So that's pretty bad. The LSM-Tree based Dockstore, to index that 1 day's worth of data takes 5 minutes. And honestly, so that's 5 minutes to index it and put the jobs into the memcache. The bottleneck there is actually memcache. So I don't know what the actual write time is. Maybe it's like a minute to actually update the index. And it's been in production for a year, and it's been doing well, and it's good. I don't really see a need to revisit this problem in the near future. And then sort of where were we? In November 2011, when we replaced this, we had about 851 million documents a day being accessed. We had 32.5 million new jobs per month. And we're seeing peaks of 14,000 jobs per second. It's kind of a big number. January 2013, 1.5 billion documents per day being accessed, 41.3 million new jobs per month. So that's increased. But then we've doubled on our throughput. So the peak is now 30,000 jobs per second being accessed. And then, so Dockstore v2, it works, job search is fast, and the results are fresh again.